Welcome back to Aurora Tech Channel. Today, I will review the QiDi Max 4, their new flagship Core XY printer. The base price is $1,049, and if you want the multi-filament box, you can add $150 to get the Max 4 combo. Let's take a look at what this machine has to offer. This is a fully enclosed machine with a large build volume of 390 by 390 by 340 millimeters. The build is robust. The net weight of the printer itself is about 90 pounds. The motion system is using linear rail on the X-axis and thicker 12mm linear rods on the Y and Z axes. The X and Y axes are using closed-loop stepper motors with a claimed top speed of 800 millimeters per second and 30,000 acceleration. The maximum nozzle temperature is 370 degrees, the bed can reach up to 120 degrees, and the heated chamber can heat up to 65 degrees. As the bed is large, it uses a 700-watt heater that can heat from room temperature to 120 degrees in about 15 minutes. The chamber is a 500-watt PTC heater, and it can heat up from room temperature to 60 degrees in about 20 minutes. The nozzle is a bimetal nozzle that comes in 0.4, 0.6, and 0.8 millimeters. The extruder is using a new design that has an inlet for an air hose. An external cooler works like an air pump and pushes cool air to cool down the gears and filament to prevent clogging. The top cover is also added with a slide-back design. You can leave a 5-inch gap to keep the internal temperature cool when printing PLA and TPU. For part cooling, besides the print head cooling fan, it also has a large auxiliary fan on the left side. For other features, it has 5-inch touchscreen, a 1080p camera, 32GB eMMC. It supports both 2.4 and 5 GHz Wi-Fi, as well as Ethernet to let you print within your local network without using any third-party cloud service. You may also use a USB drive if you want to print completely offline. It also has a 3-stage filter with HEPA and active carbon before exhausting the air into your room. For software, besides its own QiDi slicer, it fully supports the regular Orca slicer, so you can send prints and manage your printer directly in Orca Slicer device tab and access the full Fluid Web UI. I would like to thank QiDi for sending us this machine to review and for sponsoring today's video. As always, even though this is a sponsored review, I will still point out any issues or drawbacks I find during testing. This helps give potential buyers a realistic expectation and also offers useful feedback for the manufacturer to improve future firmware and software updates. With that said, let's get started. The printer arrived in a huge box, weighing over 120 pounds. The top lid lifts off, and it's still not too difficult to remove the machine from the box. The multi-filament box and all accessories were packed inside. First, I mounted the 4:1 filament hub at the back of the printer. Then I connected 4 Bowden tubes from the filament box to the hub. There are 2 cables to connect, one from the box to the hub, and one from the box to the machine. Since the filament box has a heating function, it also requires its own power cable. Overall setup is straightforward, similar to other AMS-style systems. When powering on the machine for the first time, it walks you through a setup wizard. You start by selecting the language, followed by your location. For Wi-Fi, it supports both 2.4 and 5 GHz networks. After that, it reminds you to remove all protective materials inside the machine and unlock the bed by removing a few screws. Then the printer runs a self-test. It starts with the motion system, followed by testing the heaters, including the nozzle, bed, and chamber. After that, it performs input shaper calibration, and finally a 9x9 81-point bed leveling. Before starting my tests, I updated both the printer and the filament box to the latest firmware. During my testing, QiDi released 3 firmware updates. The final version before this video is v1.1.6.1. Now let's load some filament and begin testing. The rollers at the bottom apply quite a bit of force, but you still need to close the lid for proper operation. I'm leaving it open here just for filming. The filament box supports RFID with their own brand of filaments, but since I usually use different brands, I still have to manually select the filament type and color on the screen. For the first test, I ran a standard G-code Benchy to make sure everything is working. After a few layers, once the printer reached full speed, I measured the noise level. With the door open, the sound level stays around 60 decibels. When the door is closed, it drops by about 5 to 8 decibels, staying mostly in the low to mid-50s. On the early firmware, the total print time was not displayed. The actual print took about 25 minutes, or around 30 minutes, including preparation time. Yellow PLA hides layer lines well, and the print looks quite clean. After updating to the latest firmware, I printed another Benchy using Galaxy Green PLA. This time, the screen showed about 24 minutes. Including prep time, it's still around 30 minutes total. The surface quality is still good, but I did notice some minor cooling issues at the front of the Benchy. It's not as clean as with regular PLA, but overall still a solid result considering the speed. Next, I tested multicolor printing. My first benchmark is the 4-color square test. This small model uses all 4 colors on every single layer. Even at just 5 millimeters tall, it requires 76 color changes. The estimated print time is over 3 hours, which is slower than average. Let's see how it performs in real use. I timed the color changes and displayed them on screen. The first color change is from yellow to blue, and it already seems slower than average. This first change took 2 minutes 53 seconds. I'll time a few more color changes and display all the times at the top right corner. The second change is from blue to yellow. Since this is a dark to light transition, I expect more purging in a longer time. It took 3 minutes 25 seconds, which is even slower. The third change is from yellow to skin tone. It's similar to the first one and took 2 minutes 55 seconds. Next, it changes from skin tone to white. This one took 2 minutes 40 seconds. Finally, from white back to skin tone. This should be the fastest since white doesn't contaminate other colors, but it still took 2 minutes 39 seconds. The print finished in 4 hours and 3 minutes, almost 1 hour longer than the slicer estimate. However, the filament usage estimate is quite accurate. The model itself used 5 grams, purge waste was 39 grams, and the prime tower used 4 grams. All values closely match the slicer estimate. Now let's compare this with other printers. Compared to the 2-year-old K2 Plus, the K2 produces significantly more waste due to its longer heat break, which requires more purging. The Max 4 produces less waste, but the total print time is still about 13% longer. Compared to the latest Creality Spark X-Dye 7, which retracts filament before cutting and reduces waste by nearly 50% compared to the K2 Plus, the Max 4 performs well in purge efficiency. It only uses about 6 grams more than the i7. However, the print time is about 85% longer. Compared to the 3-year-old Bambu Lab A1, purge waste is similar, but the print time is still about 60% longer. So overall, the Max 4 handles purge waste quite well, but it falls behind in filament change speed. Since I measured the heat break lengths across different printers, the Max 4 is actually the second shortest among all 4 printers, so the extra time isn't coming from purge volume. I found that loading and unloading from the filament box is much slower than other AMS variants. Excluding purging, just unloading the current filament and loading the next one from the box to the extruder takes about 1 minute and 25 seconds on average. During purging, it's also slightly slower than average. In total, each color change takes at least an extra minute, which explains why the overall print time is much longer than the other machines in this 4-color cube test, especially considering it has 76 color changes on such a small model. We'll run more multicolor benchmark prints and compare the results with other machines. It's time to expand my Hello Kitty army again. The average print time when printing 4 of them on other printers is around 18 hours, and the slicer estimate on this Max 4 is 18.5 hours, but I don't think that's realistic. Based on the last test print, each color change takes at least 1 minute longer than expected. For this print, there will be 314 color changes. If I multiply 314 by 1.2 minutes, that adds about 376 minutes, or roughly 6 hours of additional time due to the color change slowdown. Therefore, instead of 18.5 hours, I would expect the total print time to be closer to 24 hours. Despite the slower color changing speed, this multi-filament box is quite reliable. So far, it has completed close to 300 color changes smoothly. In the early firmware, the device tab in the slicer used a fluid web UI. However, in later updates, it was changed to a Bamboo Studio style interface. If you prefer the fluid web UI, you can still access it through a browser. The print finally finished in 24 hours and 22 minutes, about 6 hours longer than the slicer estimate. Once again, the time estimate is off, but the filament estimate is accurate. The model and supports use 204 grams, matching closely with the 210 gram estimate. The purge waste and prime tower are also spot on. Taking a closer look at these 4 Hello Kitty models, the first and second prints after a color change show some contamination. You can see yellow and black bleeding into the white areas. The last 2 look better, which suggests we may need to increase the purge volume when switching from yellow to white and black to white. Let's compare the results with other printers. Once again, the Max 4 is the slowest among all single extruder AMSO style systems. With 313 color changes and over 1 minute of additional time per change, that results in about 6 extra hours, making it roughly 4 to 7 hours slower than other machines. In terms of purge waste, it uses less than all the others. However, if I add an extra 15 grams for each black to white and yellow to white transition to fully eliminate contamination, it would still rank as the second best in purge efficiency. I also ran a few additional test models, and the results were consistent. The multi-filament box is reliable, with 0 loading or unloading issues. However, for every 50 color changes, you should expect about 1 hour of extra print time compared to other printers. For example, this Vegeta model has 247 color changes. Using that estimate, this print requires roughly 5 extra hours, even compared to the not-so-fast K2 Pro. When printing something with close to 1,000 color changes, like this Master Sword with 877 changes, it adds about 18 extra hours. With an average print time of 32 hours, it ends up taking 50 hours on the Max 4. The print quality is on par with other machines, but the speed is significantly slower. Let's move on to some other tests. Since this printer has a large 390 by 390 millimeter build area, I can run all my benchmark prints at once. Instead of printing layer by layer, I can use object by object mode. This ensures that if one object fails, it won't ruin the entire plate. However, this method requires additional clearance for the print head to move between objects. As you can see, the outlined area shows the required spacing, and even this large build plate can barely fit all 4 models. The estimated time for all 4 models is 10 hours and 19 minutes. I manually timed each print and will show the breakdown. The final time was 10 hours and 22 minutes, plus 7 minutes of prep time. The number slider finished in 2 hours and 31 minutes, slightly faster than the 2 hours and 45 minutes average. The Honeycomb box took 2 hours and 23 minutes, also faster than the 2 hours and 40 minutes average. The tolerance test took 1 hour and 22 minutes, slightly faster than the 1 hour and 30 minutes average. Finally, the Robo Alpaka finished in 4 hours and 7 minutes, faster than the usual 4.5 hours. For the number slider, the top surface is decent, the bottom is excellent, and all tiles move freely. The Honeycomb box is printed very well, with all side patterns intact and no breakage. The bottom adheres well, and the patterns are printed very cleanly. Even compared with other high-quality printers, the Max 4 delivers one of the best results. When comparing bottom surface quality, the Max 4 is even better than some of them. For the tolerance test, it clears down to 0.05 millimeters and stops at zero clearance on the square side. On the cylindrical side, it also clears down to 0.05 millimeters and stops at 0, achieving a perfect score on both sides, although the text shows some ghosting. The Robo Alpaka was also printed beautifully. Let's look at it from all 4 angles and compare it with other machines. Compared with the Bambu Lab H2C, the H2C is slightly faster, but the Max 4 has marginally better print quality. Compared with the Prusa Core 1, the Max 4 is faster and also produces better surface quality. Compared with the Creality K2 Pro, the print times are similar, but the Max 4 has noticeably better surface quality. Compared with the fastest Core XY I've tested, the K2 Plus is still faster than almost everything else, but the Max 4 again shows slightly better surface quality. Next, I tested different materials, starting with PETG. The Auto Z offset was set at a nozzle temperature of 140 degrees Celsius, which works perfectly for PLA. However, for higher temperature materials, thermal expansion requires manual adjustment. I restarted the print and added 0.05 millimeters to the Z offset from the screen menu to compensate. Unlike a bed slinger, you need to move the bed down to increase nozzle clearance on a Core XY. As expected, the first layer for PETG is now perfect. The print finished in 4 hours and 52 minutes, and the quality is consistent from bottom to top. Next, I tried TPU. I experienced feeding issues with standard 95 ATPU when using the filament box, which is not surprising since long Bowden tube paths are not ideal for flexible materials. I switched to a spool holder and fed the filament directly into the machine. This large door stopper printed very well, finishing in 2 hours and 44 minutes with excellent results. Then I tested engineering-grade materials, starting with PCABS. I set the chamber temperature to 60 degrees Celsius, which reached about 58 degrees Celsius in 25 minutes before printing started. For the Z offset, I increased it to 0.075 to further compensate for the higher printing temperature. The total print time was about 3.5 hours, including 30 minutes of prep time. Despite reduced cooling causing minor imperfections, the print adhered well with zero warping, and the bottom surface looks excellent. I also printed the same model using ABS glass fiber, which tends to clog 0.4 millimeter nozzles and is difficult to use in AMS-style systems. The Max 4 also handled it very well, producing results similar to PC ABS without issues. Finally, I tested PPS-CF. The recommended nozzle temperature is 300 to 370 degrees Celsius. At 300 degrees Celsius, it printed, but the layer adhesion was poor. The part broke when dropped from about 6 inches. So I will use the maximum temperature of this printer at 370 degrees Celsius and see if we can achieve better results. The print finished in 3 hours, and the PPS-CF phone holder turned out excellent. Using a 370 degrees Celsius nozzle temperature significantly improved the results. The parts sound more like metal than plastic. The challenging part was installing a 1/4 inch copper threaded insert. Since the material softens around 280 degrees Celsius, I had to set the soldering iron to 400 degrees Celsius and apply significant pressure. Printing at 370 degrees Celsius unleashes the strength and stiffness of the PPS-CF filament, and I expect this phone holder to last a long time. Okay, let's talk about the pros and cons of this printer, starting with the pros. 1. The build is robust, with the machine itself weighing 90 pounds and the full combo package exceeding 120 pounds. The hardware specs are also strong, featuring a linear rail on the X-axis and thick 12mm linear rods on both the Y and Z axes. The bed uses a 700-watt heater that can reach 120 degrees in about 15 minutes, while the chamber has a 500-watt heater that can reach 60 degrees in about 20 minutes. 2. The 370-degree high-temperature nozzle, along with a 120-degree bed and a 65-degree chamber, makes this an excellent setup for printing ABS-based filaments. I tested PC ABS, glass fiber ABS, and flame retardant ABS, all with excellent results. I also printed PPS-CF at the maximum temperature of 370 degrees and achieved significantly better results compared to printing at 300 degrees on other machines. 3. The massive build volume is very useful. It not only allows you to print larger objects, but also lets you print multiple items on the same plate using by object mode instead of by layer. This mode requires a larger build area because additional clearance is needed for the print head. This way, it prevents a single model failure from ruining the entire plate, minimizes downtime from manually swapping prints, and saves about 5 to 7 minutes of prep time for each job. 4. It fully supports Orca Slicer. Within the Device tab, you can access the full Fluid Web UI, which provides additional controls for advanced users. This is a big advantage for anyone who doesn't want to install another variant of Orca Slicer on their computer. 5. The external cooler helps reduce the temperature around the extruder and allows the filament to cool before entering the heat break. It may not sound very useful, but if you've tried printing in a hot garage during the summer, even PLA can clog on partially enclosed printers. Last week, when my garage temperature was close to 34 degrees, the nozzle clogged halfway through printing the Vegeta model. It clogged again after restarting the print, so I added the external cooler, which is essentially a combination of an air assist pump and a thermoelectric cooler that sends cooled air through a hose. When I checked the outside of the hose, it was about 10 degrees cooler than surrounding surfaces, and the print was finally completed successfully. So I do think it makes a noticeable difference, but the cooler has its own disadvantages, which we'll discuss later. Now for the cons. 1. The multi-filament box operates slower than other options on the market. Based on multiple multicolor test prints, I timed the color changes and found that this system requires an additional 60 to 70 seconds per change compared to other AMS-style systems. That means for a print with 50 color changes, you can expect it to take about 1 hour longer than most other machines. This isn't a major issue for simple models like a 4-color Benchy or an Among Us model with minimal color changes. However, for more complex prints with close to 1,000 color changes, the difference becomes significant. 2. The 4:1 splitter is mounted at the back of the machine rather than integrated into the box like the Bambu Lab AMS. I don't think most users would use a single extruder AMS style system to print 16 colors unless they're willing to deal with purge waste that can use 5 to 10 times more filament than the model itself. It's hard to imagine how messy it would get with 16 Bowden tubes and multiple splitter hubs hanging off the back of the machine. 3. The extruder cooler is an interesting new idea. However, if the air hose isn't positioned correctly, it can interfere with or bend the Bowden tube, which could make the already slow filament changing process even slower. When the printer fails to feed filament, it keeps retrying by moving to different positions. You also need a tray to catch the water dripping from the unit, which isn't very practical in a clean office or home environment where you wouldn't expect to deal with dripping water. In conclusion, the Max 4 has some of the most robust hardware in its class and can reach higher temperatures than most consumer-grade 3D printers on the market. This machine is ideal for users working with engineering-grade filaments, printing various types of ABS, or requiring a stable ambient environment with a large build volume. If you use it as a single extruder standalone machine, it offers a strong value for a $1,000 printer. However, if your focus is multicolor PLA printing, there are many better options available. You can likely spend $300 to $500 on a much cheaper machine that performs better for multicolor prints. I'm not sure whether the filament loading and unloading speed can be improved at the firmware level without affecting reliability, but I do hope to see improvements in future updates. The box itself is pretty affordable, as you can add it to the combo for just $150, and it's capable of drying filament at up to 65 degrees. However, the speed of the multi-filament box remains as the main drawback of the overall setup. If you're interested in the QiDi Max 4, I included the link in the video description. Don't forget to also check out AuroraTechChannel.com, which tracks prices for popular 3D printers, laser engravers, and CNC machines to help you find the best deals. That's it for this video. If you found this video helpful, please give it a like and consider subscribing to our channel. Thank you for watching, and I will see you next time.